Laboratory experiments will require you to analyze the data you acquire, or maybe even create a system model based on the acquired data. MATLAB is ideal for those types of tasks. In this video, I'll talk about MATLAB syntax and user interface. I won't assume that you have any familiarity with MATLAB itself, but I will assume you have some programming background. Matrix operations and linear algebra are central to use of MATLAB. I'll also assume that you're familiar with those topics.
When MATLAB is first opened, you see what is called the desktop. The desktop is the primary interface with which a user interacts with MATLAB. The first time you open MATLAB, the desktop should look pretty much as it's shown here. There's a tool strip across the top of the desktop. Its buttons provide access to some very convenient MATLAB capabilities. The current folder window is on the left of the desktop. This window shows the files and folders that are in MATLAB's current working folder. Keeping track of the current working folder and its contents is very important. The current working folder is one of the primary places that MATLAB looks when we ask it to find something. It's also one of the primary places where MATLAB will save information if we want to write data to disk. The path to the current working folder is shown in this text bar. If desired, we can change the current working folder by clicking on this icon and browsing to the desired location. As with Windows Explorer, we can use the current working folder window to create or remove folders. To create a folder, right-click with your mouse button in the current folder window and select New Folder. I'll create a new folder named Temp in this folder. To remove a folder, right-click with your mouse on the folder and choose Delete from the resulting menu. This is the workspace window. The workspace is where MATLAB stores the results of any computations. I haven't done any calculations yet, so nothing's displayed in the workspace window. In the lower right corner of the desktop is the Command History window. This window simply displays the commands that have been executed in MATLAB in the order in which they were executed. Again, since I haven't executed any commands yet, there aren't any commands listed. Finally, the command window is this big window in the center. MATLAB commands are typed at the command prompt, the two greater than signs here, and are executed by pressing the Enter key on your keyboard.
All variables in the workspace have to have a name. Those names have to adhere to some specific rules. MATLAB variable names have a maximum of 63 characters. The first character has to be a letter. Variables cannot contain spaces, punctuation, or mathematical operators. And most special characters are not allowed, but underscores are okay. Finally, MATLAB variable names are case sensitive. Arrays and matrices are incredibly important in MATLAB since the entire program is geared towards using groups of numbers. MATLAB provides a variety of ways to create arrays. The first approach I'll go over is creating an array by specifying individual elements. When defining an array, enclose the array elements in square brackets and separate columns by either spaces or commas. Rows are separated by semicolons or an enter keystroke. For example, I want to create this matrix with the variable name b. I first type the variable name b, followed by an assignment operator, an open square bracket, then the elements in the first row, a 1 and a 2 separated by either a number of spaces or a comma. A semicolon moves me to the second row. I can enter those elements here. Another semicolon moves me to the last row, and I can input a 5 and a 6, again separated by either spaces or a comma. A closed square bracket terminates definition of the array. Pressing the Enter key evaluates this and defines the variable in the workspace. Arrays can also be created with what is called colon notation. The syntax is you provide it with a beginning value, which I'll call start underscore val, followed by a colon, an increment, another colon, and an ending value. The first element in the array will always be start underscore val. Successive elements change by the amount increment from the previous element in the array. And the process is discontinued when the next value exceeds in underscore val. So, for example, x equals 0.2 colon 0.3 colon 0.9 sets x equal to the first element is 0.2. The next element is 0.2 plus the increment, which is 0.5. The next element is 0.5 plus the increment, which is 0.8. The next element would be 0.8 plus 0.3, which is 1.1. However, that's larger than 0.9, so we terminate creation of the array here. MATLAB has a variety of functions for creating arrays. I'll run through a few examples here. Linspace creates an array of uniformly spaced values. Logspace creates an array of logarithmically spaced values. Zeros creates an array of zeros, and ones creates an array of ones. EYE creates an identity matrix. RAND and RAND-N create arrays of random numbers. RAND creates uniformly distributed random numbers, and RAND-N creates normally or Gaussian distributed random numbers. Syntax and usage of the above are available in MATLAB's help files. Check those out if you need to use these. For this demo, I'll work directly in the command window. First, I'll create an array named A. A equals, open square bracket to indicate an array, 1 space 2 space 3, semicolon moves me to the next line down, 4 space 5 space 6, another semicolon moves me to the third row, 7 space 8 space 9. Close the square brackets and press enter. I'll also create an array B equal to 0. I'll use a comma to separate the columns here. So 0, comma 1, semicolon 2, comma 1, semicolon 3, and I'll use a bunch of spaces and then a 0. Close the square brackets. Notice that it doesn't matter whether I use spaces or commas to separate the columns. It also doesn't matter how many spaces are used when separating columns. Next, I'll create an array named x that starts at 0, has increments of 0.2, and ends at 1. So x equals 0, colon, 0.2, colon, 1. Finally, I'll create a 3 by 3 vector of 1s by typing C equals 1s of 3. If I give my matrix creation commands a single argument, the number of rows and columns in the matrix are the same. I can create non-square matrices by giving the command 2 arguments. So D equals rand_n of 3, comma 2 creates a 3 by 2 matrix of normally distributed random numbers. Accessing elements of an array in MATLAB is done in the same way as most computer languages. You simply specify the row and column of the element you want in parentheses after the variable name which defines the array. One-dimensional arrays require only a single number. In MATLAB, ranges of elements can be accessed using colon notation. The syntax is similar to what's used when specifying arrays using colon notation. Provide the first element you want, a colon, the increment between elements, another colon, and the final element. If you don't specify an increment, MATLAB will assume that it's 1. Array addresses in MATLAB are always positive integers. The first element in a MATLAB array has an address of 1. This is unlike C programming, in which the address of the first element in an array is 0. Now I'll talk about MATLAB's arithmetic operators. There's a pretty long list of them. Plus and minus do addition and subtraction. Multiplication can be done either by an asterisk symbol or an asterisk symbol with a dot in front of it. It's a period key on your keyboard. Division is either a forward slash or a backward slash. Those also both have dotted versions. Exponentiation is a caret symbol or a caret with a period in front of it, which I'll generally refer to as a dot. The precedence of these operators is just what you would expect. Exponentiation is done first, multiplication and division are next, and addition and subtraction get done last. Within the same precedence, operations are done left to right. You can override any of that with parentheses. Most of MATLAB's operators come in two versions: array operators and matrix operators. The commands with dots or periods in front of them are array operators. This means that the operations are performed on corresponding elements in the operand arrays, and the result is placed in the corresponding location in the resulting array. This is also called an element-by-element operation, since operations are done between corresponding elements of the arrays. The operators with no dot perform matrix operations according to the rules of matrix algebra. Matrix addition and subtraction are the same as element-by-element addition and subtraction, so there's no dotted version of those two operators. In array operations, both of the operands have to have the same number of rows and columns. In matrix operations, the matrix sizes have to be consistent with the rules of matrix algebra. For example, to perform a matrix product, the inner dimensions of the matrices have to agree. Since array sizes are so important, MATLAB has a number of commands that display array sizes. Length returns the number of elements in a row or column vector, while size returns the number of rows and columns in that order in an array. The total number of elements in an array can be determined with the numl command. Now I'll demonstrate some matrix operations. I still have the arrays in my workspace that I created in the last demo. A and C are both 3x3 arrays, so I can multiply them using dotted operators. So A dot times C. Since C is an array of ones, I'm just multiplying every element of A by 1. So the result is the same as the original A matrix. A and C also have matching inner dimensions, so I can take the matrix product between the two. So A asterisk C. A and B are not the same size, so I can't do an array multiplication between the two. So if I type A dot times B, I get an error. I can extract pieces or elements of any given array. To get the first two columns of A, I can type A of colon. This will return all the rows, comma, 1 colon 2. And this will give me columns 1 and 2, all the rows. MATLAB has amazing plotting capabilities. I'll just cover some of the very basic techniques in this video, but I strongly suggest you use MATLAB's help files to learn more advanced applications. The most fundamental plotting command is plot. Plot allows you to create two-dimensional plots with multiple sets of data and a wide variety of line styles. The syntax is the function name, plot, followed by vectors containing the x and y data of the first line on the plot, and a line specifier defining the properties of that line. Additional lines are specified similarly. So x2 and y2 are the data points for the second line, and linspec2 provides the properties assigned to the second line, and so on. As I've indicated, linspec1, linspec2, and so on specify the properties of the line. The simplest properties are the line color, style, and markers for data points, but you can customize virtually anything about the line or the data markers. You can also easily annotate plots. Axis labels can be added with the X label and Y label commands. The title command adds a title to the top of the plot, and plots with multiple lines should include an annotation describing each line, which can be done with the legend command. I don't need the arrays from the last demo, so I'm going to delete them from the workspace using the clear command. To clear all the variables, type clear all. Individual variables can be removed by typing clear and then the variable name. Now I'll create some data to plot. The function will be y of t is equal to 3 times e to the negative t over 2 times the cosine of 4t. I'm going to plot that from 0 to 10 seconds. First, I'll create an array of times using colon notation. So t equals 0, colon, 0.01, colon, 10. I'll follow this with a semicolon. That will suppress display of the results of this command. Then I'll create the function itself. So y equals 3 times exp of negative t over 2 dot times cosine of 4 times t. I need a dot times here because I'm doing an element by element multiplication. To plot the values of y at the time point specified in t, use the plot command. So plot of t, comma, y. When I press the Enter key on my keyboard, the plot is created in a figure window. If there aren't any open figure windows, the plot command creates one. If there are open figure windows, the plot command uses the currently active window, which is the last figure window that was used. In this simplest form of the plot command, the first argument is a vector containing the points on the horizontal or x-axis, and the second argument contains the points on the vertical or y-axis. Now create another function and plot it. The new function will be z equals 5 times t dot times exp of negative t. I'll use the same time vector I used before. Now if I plot z by typing plot of t comma z, I get a plot of the new function, but my old plot's lost. MATLAB's plot command puts the new plot in the currently active figure window, the one I created with my last plot command. If I want to create a separate figure window for my second plot, I can use the figure command. To create the new figure window, I type figure and press the enter key on my keyboard. This opens a new figure window. The new figure is the active figure window, so to plot the original function, I type plot of t, comma, y, and press enter. Now I have two figure windows, each of which shows one of the functions I wanted to plot. Now I'll create a figure with both lines on it. I'll type figure to create another figure window, and then type plot of t, comma, y, comma, quote k, close single quote. That gives me a black line. Comma, t, comma, z, quote, r, colon, which will give me a red dotted line. Pressing enter, I get this figure. To add labels to the x-axis, I can use the xlabel command. So xlabel of time, comma, seconds. The string inside the argument defines the label on the axis. Single quotes denote a string in MATLAB. I'll press enter to add the label. Take another look at the plot. Similarly, I can add a label to the y-axis with the ylabel command. So ylabel of data values. To add a legend, I'll type legend of y data. That'll be the label on my first data set, comma, z data, which is the label on the second data set. The legend command displays an example of the line style used for the data along with the corresponding label. In my demos so far, I've just been executing commands at the command prompt in the command window. This is okay for simple calculations, but it can be a really inefficient way to use MATLAB when you're doing fairly involved multi-step calculations. In these instances, it's easier to use a script file to execute your commands. A script file is simply a text file that contains a series of commands you want to execute together as a group. Script files have a .m extension, so they are one type of what is called an M file. The other type of M file is called a function file. Script files use the same workspace that's used when we execute commands at the command prompt, which means that the effect of the commands is exactly as if you typed and executed them sequentially at the command prompt. Function files each have their own workspace. This means that you can create variables in functions without worrying about whether they'll overwrite variables that already exist elsewhere. To demonstrate how to create and use script files, I'll first set up a new working folder. I can click on the Browse button up here, navigate to the TIM folder on the C drive, and create a folder named Demo. This folder is now my current working folder. I'm going to use a script file to create the same functions and plot as I did in my previous demo. So before I create the script file, I'll get rid of my old work. I can clear my workspace by typing clear all. I can also close my existing figures by typing close all. Now I'll create a script file by clicking on the new script button. I'll create the same functions and plot from my previous demo. When I click Save, the Save dialog box defaults to the current working directory. MATLAB knows where this folder is, so I can just give the file a name, test file, and click on Save. Names for files follow pretty much the same rules as names for variables. Now just click Run to run the file. The file executes and the plot is created. Finally, I'll introduce how to import data into MATLAB. MATLAB can import data from a wide variety of formats, and will also export data to those formats. Most oscilloscopes save data in either tab-delimited text or comma-separated variable formats. So those are the formats I'll emphasize here. I will, however, mention in passing that the load and save commands can be used to import and export files that are in MATLAB's native binary format. The simplest use is simply the command load or save, followed by a space, and then the name of the file you want, without an extension. This approach loads or saves a file with a .mat extension of the specified name from the current folder. To load text files, the simplest approach is to use the load command as above, but with an extension on the file name, then another space, and a -ASCII specifier. This will load an ASCII file of the specified name from the current folder. The data will be saved in an array with the name file name, but no extension. Since the data will be in an array, the file can contain only numbers and must have the same number of columns in every row and the same number of rows in every column. To load comma-separated variable files, it's easiest to use the CSV read command. To learn more about CSV read, look at MATLAB's help files. Some other examples of import functions are XLS read, which loads data from a Microsoft Excel file, IM read, which reads image data, and audio read, which reads audio files. There's a lot more, but if you look at the help files for these, they'll lead you to the related functions. I used an acoustic proximity sensor to measure the position of a falling mass. I saved the data in a text file named droptest.txt in my current folder. If I use the load command, MATLAB will load this data into an array. This means that all of the elements in the table have to be numbers, all of the rows need to have the same number of columns, and all the columns have to have the same number of rows. So before I try to load the data into MATLAB, I'm going to open it using Notepad. The oscilloscope I used to measure the data adds some headers into the file. I'll delete those and save the file again before importing the data into MATLAB. Now I'll load the file by typing load droptest.txt space dash ASCII. An array gets created named droptest. The first column of the array is time, and the third column is the position of the mass. I can plot the position as a function of time by typing plot droptest of all the rows, comma, the first column, comma, droptest of all the rows, third column. Since this is data, I should put a symbol at each data point. I'll use red circles. This is the position of the mass as it falls. There are a lot of data points, but I can see individual data symbols by zooming in. The tools presented in this video should allow you to import measured data into MATLAB, extract portions of that data within MATLAB for analysis, perform calculations based on that data, and plot your data relative to expectations. All of these skills are essential for any kind of lab work.